Hello. Earlier we have learnt about the differential calculus in vectors. We have learned the operations like gradient, divergence and curl. And we have also learned second order derivatives. Now we will work out some examples involving gradient, divergence, curl and second order derivatives. Those of you who are already familiar with these things and have worked out a lot of examples, have solved a lot of problems, you can skip this part. It would be useful for others. I would nevertheless recommend everybody to go through this part as well. So let's start. Let's consider few problems, few examples, and let's work that out. In the first example, we consider a gradient. We take the del operator operating on the position vector magnitude power n, and if we do that, we are supposed to show that this quantity is equals n times r power n minus 2 times r vector. This is the gradient. That's something we are supposed to prove. Let's work it out. The gradient of r power n can be written as the gradient of x square plus y square plus z square square root. This is the magnitude of the r vector, position vector, and this one power n, which is nothing but the gradient of x square plus y square plus z square power n over 2. This with the gradient operator can be expressed as x cap del x of x square plus y square plus z square power n over 2 plus y cap del y of the same thing plus z cap del z of the same thing. Now, if we work this out, if we work out the derivatives, we will find that this quantity is equal to x cap n over 2 x square plus y square plus z square power n over 2 minus 1 times twice of x plus y cap times similarly n over 2 x square plus y square plus z square power n over 2 minus 1 multiplied by 2y plus z cap n over 2 x square plus y square plus z squared n over 2 minus 1 multiplied by twice z. This is the quantity. If we now simplify this, we will arrive at this quantity is equal to n times x square plus y square plus z square power n by 2 minus 1 times x cap plus y cap plus z cap, and this is nothing but n This quantity is position vector square r square power n by 2 minus 1 times r vector, which is n times r power n minus 2 r vector. It's essentially n r power n minus 1 r cap, the r cap being the unit vector along the direction of r vector, the position vector. Okay, let's see the second example. In the second example, we have the equation of two surfaces and we are supposed to find the angle between these two surfaces. So, the statement of the problem is find the angle between the surfaces given by z equals x square plus y square and z equals x minus square root 6 over 6 square plus y minus square root 6 over 6 square, and the angle is to be found at a given point P with the coordinates square root 6 over 12, square root 6 over 12, 1 over 12. This is the coordinates of the point. So, how do we find the angle between two surfaces? The direction of the surface is given by the normal to the surface. And how do we find the normal to this surface? Let us see. If we consider two functions phi 1 and phi 2, phi 1 is given as x square plus y square minus z, and phi 2 is given as x minus square root 6 over 6 square plus y minus square root 6 over 6 square minus z. Then if we have these functions, then we can say that the normal to the surface given by z equals x square plus y square, that means the normal to the first surface can be given by the gradient of phi 1, and if we work out the gradient for this function phi 1, we will find that gradient of phi 1 equals 2x x cap plus 2y y cap minus z cap, and this is pretty obvious. Then if this is the gradient, then the gradient of phi 1 at point P with the coordinate of the point P given earlier is nothing but square root of 6 over 6 x cap plus square root of 6 over 6 y cap minus z cap. Similarly, we will have to find a normal to the second surface. The second surface is given by z equals x minus square root 6 over 6 square plus y minus square root 6 over 6 square. This one would be given by gradient of phi 2, and that is, if we work it out, we will find twice x minus square root of 6 over 6 square x cap plus twice y minus square root 6 over 6 square y cap minus z cap. This is the gradient, and if we now try to find the gradient at point P, that is gradient of phi 2 at point P, that is given as minus square root of 6 over 6 x cap minus square root of 6 over 6 y cap minus z cap. Now we are supposed to find out the angle between these two vectors. So what are we supposed to do? Let's take a dot product of the gradient of phi 1 at the point P with the gradient of phi 2 at the point P. And this quantity is equal to the magnitude of the gradient of phi 1 at point P multiplied with the magnitude of the gradient of phi 2 at point P times the cosine of the angle between these two vectors. So the dot product, let's calculate the dot product in its component form first. Square root of 6 over 6 x cap plus square root of 6 over 6 y cap minus z cap, this vector dotted with minus square root of 6 over 6 x cap minus square root of 6 over 6 y cap minus z cap. So this gives us minus, from the first term we get 6 over 6 square, that is 1 over 6. From the second term also gives the same, minus 1 over 6, and the third term is plus 1. So this is the value of the dot product we get. And if we now work out the magnitude of the vectors, then the magnitude of the vectors will be nothing but both vectors have the same magnitude, and that would be square root of each the sum of each component squared. So the magnitude of phi 1 at P equals to the magnitude of the gradient of phi 2 at the point P and that is 1 over 6 plus 1 over 6 plus 1 square root of this. So, we can write down that after working this out, we will find that cosine of the angle between these two vectors, that is cos theta, is half. And if cos theta is half, then theta is cos inverse of half, and that is 60 degree. So, 60 degree is the angle between these two vectors. Let us move on to another example. That is example 3. Example 3 involves evaluating the Laplacian of 1 over the position vector. So, let us try evaluating this. The position vector, 1 over the position vector is given as 1 over x square plus y square plus z square, square root of this, and we know the del square operator. Del square is del 2 del x2 plus del 2 del y2 plus del 2 del z2. So, this quantity would be del 2 del x2 plus del 2 del y2 plus del 2 del z2 of 1 over square root of x square plus y square plus z square. Now, let us calculate each part of it separately. If we perform the first partial derivative, del x of 1 over square root of x square plus y square plus z square, what do we get? We get this is nothing but the power of x square plus y square plus z square becomes minus half x square plus y square plus z square minus half. This helps us evaluating it, and if we now evaluate, we will find that this quantity is minus x times x square plus y square plus z square power minus 3 by 2. If we now perform the partial derivative once more, that is del 2 del x2 of 1 over x square plus y square plus z square, square root of this, we will get del x of minus x square plus y square plus z square power minus 3 by 2, and this turns out to be 3x square x square plus y square plus z square power minus 5 by 2 minus x square plus y square plus z square power minus 3 by 2. And this can be written in a compact form as 2x square minus y square minus z square divided by x square plus y square plus z square whole power 5 by 2. Now, with similarity, we can write that del 2 del y2 of 1 over r, this would be 2y square minus z square minus x square over x square plus y square plus z square power 5 by 2, and del 2 del z2 of 1 over r is similarly equal to 2z square minus x square minus y square over x square plus y square plus z square power 5 by 2. So, in order to get the result, we have to add all these terms. That means del 2 del x2 1 over r plus del 2 del y2 1 over r plus del 2 del z2 1 over r. And looking at the expressions for this, we see that this will become 0. So that means the Laplacian of 1 over r is 0, but there is a note of caution. This is 0 only when r is not equal to 0. If r goes to 0, then we will have to be more careful. This may be something else, and we will see that kind of an example somewhere else. Okay. Now, let's consider another example. Before considering another example, let's get introduced to a term, solenoidal. Solenoidal means the divergence, if the divergence of a vector becomes 0, then the vector is called solenoidal. And here in this example, that is example 4, we are given a vector v minus 4x minus 6y plus 3z x cap plus minus 2x plus y minus 5z y cap plus 5x plus 6y plus az z cap. Now the question is, now we are asked to find A so that the vector is solenoidal. Obviously, the approach would be to equate the divergence of this vector to 0, and in order to do that, we will have to find the divergence of the vector first. Divergence of v is given as del x of the x component of the vector, that is minus 4x minus 6y plus 3z plus del y of the y component minus 2x plus y minus 5z plus del z of the z component 5x plus 6y plus az, and that becomes, so from the first term we get minus 4 and the rest becomes 0 because those are not functions of x. From the second term we get plus 1 because the coefficient of y is 1 and the rest doesn't matter, those go to 0. And from the last term we get plus a, that is minus 3 plus a. So in order for the vector to be solenoidal, we need divergence of v equals 0. That means minus 3 plus a equals 0. This implies that a equals 3. This is the condition for the vector to be solenoidal. Let's move on to another example. Example 5. Here we are supposed to find the curl at a given point. So we have been given a vector A that is expressed in the component form as x square z square x cap minus 2y square z square y cap plus x y square z z cap. We are asked to find the curl of this vector at the point the coordinates of the point is given 1 minus 1 1. So we know how to express curl in its determinant form, that is x cap y cap z cap del del x del del y del del z. The x component, that is x square z square. Here is the y component, minus 2y square z square. Here is the z component, x y square z. If we evaluate this determinant, we will get the curl, and we can evaluate it to find del del y of x y square z minus del del z of minus 2 y square z square x cap minus del del x x y square z minus del del z x squared z squared y cap plus del del x minus 2y square z square plus del del y x square z squared, and z cap is the direction. Now in the last term we can see that this is not a function of x, and the partial derivative with respect to x will go to 0, and this is not a function of y. So the partial derivative of this quantity with respect to y will go to 0. We will have no z component for this curl. Okay, so with this we can write that the curl becomes 2xyz plus 4yz squared x cap minus y squared z minus 2x squared z y cap. Now, at the given point P, we are supposed to evaluate it. So, the curl of A at point P equals 1 minus 1, 1. This will become 2x cap plus y cap. This would be the value of the curl at the given point. Let's consider another example. This was example 5, so we will have example 6 here. A vector is called irrotational if the curl of that vector goes to 0. That means if curl of A equals 0, then we call A irrotational. Now, there are two parts of this problem. In part A, we are given a vector V as minus 4x minus 3y plus a z x cap plus bx plus 3y plus 5z y cap plus 4x plus cy plus 3z z cap. Now, we have to find the constants a, b and c so that this vector is irrotational. And in the second part of the problem, we are supposed to show that when V, the vector, is irrotational, it can be expressed as the gradient of a scalar function. Earlier we have learned that the curl of the gradient of a scalar field is always 0. Now here we are supposed to prove that if the vector V as expressed here is irrotational, it can be expressed as the gradient of a scalar function. So, in order to solve this problem, let us attempt the part A. In part A, the first thing is to evaluate the curl of this vector V, and this would be given in the determinant form x cap y cap z cap del del x del del y del del z minus 4x minus 3y plus az bx plus 3y plus 5z 4x plus cy plus 3z. If we work out this determinant, we will get, after carefully working this out, we will find c minus 5 x cap minus 4 minus a y cap plus b plus 3 z cap. Now, for the curl to be 0, each component of the curl has to be 0, and that will give us, for the vector v to be irrotational, c must be equal to 5, a must be equal to 4, and b must be equal to minus 3. That will only satisfy the condition. That means the vector v, when irrotational, would be given as minus 4x minus 3y plus 4z x cap plus minus 3x plus 3y plus 5z y cap plus 4x plus 5y plus 3z z cap. Now, let us solve part B. In part B, we assume first that the vector v is given as the gradient of a scalar function phi, which means del phi del x x cap plus del phi del y y cap plus del phi del z z cap is the vector v, and that will require each component of this gradient matches each component of vector v, then only this will be satisfied. So, from the form of vector v written above, we can write del phi del x equals minus 4x minus 3y plus 4z. Del phi del y can be written as minus 3x minus 3y plus 5z, and del phi del z is given as 4x plus 5y plus 3z. Now, if we partially integrate them term by term, that means in the first case, when it is partial derivative of x, we partially integrate phi, adding a function of y and z as the integration constant with respect to x. That means from the partial derivative of x we can get phi equals minus 2x square minus 3xy plus 4xz plus the constant of integration in x that may in general be a function of y and z. Similarly, from the partial derivative of y, we obtain by partial integral phi is minus 3xy plus 3 by 2y squared plus 5yz plus an integration constant with respect to y that is in general a function of x and z, and from the partial derivative of z, partially integrating that part, we will obtain phi equals 4xz plus 5yz plus 3 by 2z squared plus an integration constant which is in general a function of x and y. Now, we need to compare these three equations and get a form for these integration constants that are in general function of the variables that are not there in the partial derivative. And by comparing, we can guess that the form of fyz may be given as 3 over 2y squared plus 5yz plus 3 over 2z squared. Similarly, gxz may be given as minus 2x square plus 4xz plus 3 by 2 z squared, and hxy, this can be expressed as minus 2x squared minus 3xy plus 3 by 2 y squared. Once we have this, we can again compare which are the terms we have counted multiple times and then correct for that. After correcting for everything, we will obtain the expression for phi equals minus 2x squared plus 3 by 2 y squared plus 3 by 2 z squared minus 3xy plus 4xz plus 5yz. So, if we have this quantity phi as a scalar, and if we take the gradient of this scalar, we will get the vector v for which the curl will be 0. So, we have obtained the scalar quantity from which we can find the irrotational vector. That means we can express the gradient of phi equals the vector v, which means phi can be written as the scalar potential for v. That means if we have any irrotational vector field, it can be represented by a scalar potential.